So from this point forward in the videos for Unit 12, we're going to focus on how the heck do we fix these problems with respect to micronutrient toxicities, like you see in this picture here. And I'll give you some basics, and then I'm going to give you some applied research information that you may or may not be interested in, but I'm going to share with you nonetheless. And so how do we fix these problems? For iron, zinc, manganese, and copper toxicities, how the heck do we fix these problems? Oftentimes, when we see toxicities with respect to these four micronutrients, this occurs in acidic soils, where concentrations of iron, zinc, manganese, and/or copper are toxic to plants. So how do we fix these? You've learned about this already, actually. You have learned that when you lime a soil, that raises the pH, and these elements or nutrients become less available to plants. You already know this. So this is exactly what we do, plus a little bit extra, to fix these problems in acidic soils. In the case of toxicities where we find these, we typically find these in areas that have been historically mined, and the mining materials left or remaining on-site or off-site generate acidity. And so this is what we do. And you've learned about this already when we've talked about liming acid soils. This is an illustration of liming acid soils on steroids, right? So in these situations, we follow a very similar approach to what you've already learned in this course. So first, you account for active acidity. And second, you account for buffer acidity or potential acidity. Points number 1 and 2 are identical to what you've learned previously. The third point is different. And the third point is that you need to account for different forms of sulfur that are present in either the soil or the geologic material that's in a particular location, like you see in the bottom left-hand corner, right? And so why do we need to account for different forms of sulfur? We need to account for different forms of sulfur, especially sulfur in the form of sulfide, because sulfide is reduced sulfur, and when it's exposed to the atmosphere and water, it is oxidized and it forms sulfuric acid. And sulfuric acid is an acid, and it degrades rocks and minerals that contain iron, zinc, manganese, and copper. The pH of the system is reduced, and these four nutrients or metals, because they're released to the environment, become more toxic to plants. And so we take into account the amount of sulfides present, and those sulfides are actually fool's gold. All right, so if you see the picture in the bottom right-hand corner, and many of you have likely seen fool's gold, you think it's gold, but it's not. It's fool's gold. It's iron sulfide. And iron sulfide in the picture on the bottom left-hand corner is present in these soils. And when fool's gold oxidizes, the sulfur, elemental sulfur or sulfide in fool's gold, becomes sulfuric acid. And that leads to dissolution of minerals that contain iron, zinc, manganese, and copper, and other heavy metals like lead, like cadmium. So to fix this problem, we lime, account for active acidity, account for potential acidity, and then account for the amount of sulfur present. And then what we do is we add a safety factor, because you can't sample the entire field or entire location. And are you sure that you've accounted for all the sulfur that's present? So usually what we do is we determine the amount of lime based on points 1, 2, and 3, and then we multiply that by 1.25, and then we lime. And it's not stated here, but oftentimes in systems like you see in that foreground in the bottom left-hand corner picture, those soils are often lacking organic matter as well. So in addition to lime, we typically add an organic source, a carbon source, to kickstart microbial activity that forces nutrient cycling and turnover, like you've learned, throughout this course. In flooded soils, this is an issue with iron and manganese. Okay, and so how do we fix this problem? In rice, that's an issue because we flood rice. But in systems where we don't flood our crops, you simply need to reduce flooding or standing water. And we've done that. We've done a pretty good job of that in locations across the globe and in Ohio by installing drainage tiles. Or you can grow tolerant varieties, varieties that are tolerant to greater concentrations of iron and or manganese. Right. So there's some notes here, and you already know these notes. We've talked about this several times throughout this course. That remember that flooded conditions cause iron to change from a +3 to a +2 state, and that makes iron more available. And in fact, and we didn't really touch on this in this course much, but under flooded conditions, manganese goes from +4 to +3 to +2 and becomes more available. And in both of these instances, that can lead to toxicity.